Good morning, everyone. I am Shashank, and I'm a fourth-year PhD candidate working with Professor Moini at Princeton University. Today, I will be presenting my work on low-embodied carbon concrete enabled by aggregate optimization and concrete optimization. This work has been done in collaboration with NJIT and Rutgers, and is funded by Port Authority of New York and New Jersey, and it's a part of a low-carbon pilot program of PA and NYNJ. So, concrete production emits over 2.5 gigatons of carbon dioxide annually, and approximately 60% of these emissions come from the limestone calcination in the cement production, with the remainder comes from fuel combustion in cement kilns and other processes. Cement alone is responsible for 7 to 8% of anthropogenic carbon dioxide emissions, which is quite a big number for one single construction material. So, Global Cement and Concrete Association has provided a roadmap for a net zero emission by 2015, and they have provided several actions to reduce the carbon emissions in the next coming 25 years. The two of them are efficiency in the concrete production and reducing in the amount of the cement content in concrete. So there are several strategies that can be used to do that, and let's look at the two strategies that we are using in our case. First is particle packing and aggregate optimization. Basically increase the aggregate optimization, reduce the space and reduce the overall amount of the cement binder that is required, and you reduces the overall carbon emission. The second has been done quite a lot and is the partial submission of the cement with the supplementary cementitious material, and in our case we have done that with the fly ash and slag. And we have done both of these optimization techniques to see how it affects the mechanical properties and global warming potential of concrete. The global warming potential is a metric that determines the amount of the carbon dioxide emission with the production of the concrete. So we have used different type of aggregates, coarse aggregates and intermediate and fine aggregates. We had two types of coarse, Hamburg and Weldon, and two intermediate number 8 stones, Vantage and Weldon, and one clay and fine. We have done multiple experiments on different binary blends that contains coarse and fine aggregate, Hamburg and Clayton, Weldon and Clayton, and we have done 3 ternary blends. We have experimented on 3 ternary blends with Hamburg, Vantage, Clayton, Weldon, Vantage, Clayton, and Weldon, Weldon, Clayton. For the sake of brevity, and I will be just discussing one case of binary blend that contains Weldon and Clayton, and one case of ternary with Weldon, Weldon, and Clayton. The experimental characterization of packing degree was done according to the VV apparatus, which follows ASTM C1170 test method A. We used 5 kg of aggregates, and we put it in the mold, and we did a control vibration for 45 seconds, and then we measured how much is the packing degree of the vibrated aggregates. We have also used analytical characterization to understand packing degree, and we have used 2 models, AIM model and Modified Toufar model. The AIM models consider interaction of larger particles on packing of smaller based on furnace model. So it has 2 cases. The case 1 where coarse aggregates are higher in quantity compared to the fine aggregates, and the second equation is when you have a vice versa case where you have more fine particles than coarse aggregate. Modified Toufar model also consider these same parameters like again packing degrees, grain volume, and characteristic parameter, but it also consider 2 correction factors, that is KD and KS. So we have used these 2 models to understand the binary packing degree in these aggregate plants. As I said, we need some parameters in the analytical model. So the eigenpacking degree was experimentally calculated for Weldon coarse and Clayton fine. The characteristic diameter is obtained from the Rosen-Bramler particle distribution curve, which basically correspond to the aggregate diameter for the 36.8% retained particle passing. So looking at the particle packing for the binary system, these points shows the experimental data. And as you can see, it goes to a peak of around 7.7 packing degree for 50% coarse and 50% fine aggregates. Modified Toufar model shows a very good agreement with the experimental results with a very small error of 1.6%, whereas A model showed quite a deviation with the higher error of around 5%. We talking about the ternary experimental particle packing. I think Professor Sobolov also showed the same plot. We have done the experimental analysis with coarse, intermediate, and Clayton, and what we see is that we have a small region where we have very high particle packing. And the two peaks correspond to the value at 10% substitution of the coarse aggregate with the intermediate aggregates, and then you have a binary blend of 50 to 50% that we have just talked in the last slide. So yeah, we have higher particle packing for this 10% intermediate replacement, but that's not the all that we need to make concrete. We need to understand more about gradation. We need to understand more about the workability. So to do that, we have looked at the gradation analysis using power curves. They're also known as Fuller-Thompson curves. They are used to design the optimal gradations of aggregates for concrete. Power curves simply defined in terms of the diameter of the aggregate size, normalized by the maximum aggregate size, and it's basically is a function of n, that is a power size. These are very interesting to understand how the gradation is. If you have a uniform gradation, you can see a very, you can see such type of behavior. If you have a gap gradation with two type of aggregate, you see sort of this constant slope between these two slopes here, and you can understand more about the continuous gradation in these type of materials. So we plotted all binary blends, the best binary blends and the ternary blends with these power curves, and what we see is that with the binary blends, as we increases the amount of fine aggregates, we have much more denser packing, but there's also in all the three cases, we see that there's a big gap in between, and it doesn't fit exactly these power curves. So when we introduce 10% of intermediate aggregate, this gap becomes smaller, but if we increases these aggregates to the intermediate aggregates to around 20%, these curves become more aligned with the power curve. So adding a bit of 10% more can help to improve the gradation in these material. Quantitatively speaking more, we also looked at the Shilstone curves, Shilstone chart. These charts provide, these charts are basically provides a sort of understanding how the workability and gradation is in terms of different ranges. You have a gap-graded range, well-graded range, rocky, and the sandy range. It's a function of the workability factor and the coarseness factor. And as you can see, this is also depends on the amount of the cement content that you are using in your mix design. So when we put all of our optimal cases on the Shilstone chart, we see for the cement content of 392 kilogram per meter cube, we see that our optimal blends, they lie mostly in the sandy region. Adding a bit of intermediate aggregates with the case of 3 and 4, 5, 6, we see that they are still in the sandy, and then there's only one case with the 6 with 20% intermediate, 40% coarse, and 40% fine that lies in the well-graded, somewhat lies in the well-graded region. So if we reduce the amount of cement content for this optimized aggregate blend, what we can see is that we move the whole, we move this case of 6 with this 40 to 20 to 40 ratio to the middle of this well-graded range. So basically, we are reducing the amount of the cement by increasing the amount of the intermediate aggregate. At the same time, this also has a packing degree of 76.3, which is very close to our best case of 78.1. So for the aggregate optimization, we went with this particular volume ratio for our optimized aggregate, as an optimized aggregate blend case. Okay, we have our aggregate blend. What do we do next? We make concrete out of it. So we have 6 cases. This work has been done by NJIT. So we have 6 cases, one with the fly ash with the 30% replacement, and then with the 40% replacement, and then we have a slag 50% replacement case, and all of these cases are also with these standard aggregate blend, and we have an optimized aggregate blend case. One thing to notice here is that we reduce the amount of cement in the optimized aggregate case as we increases the aggregate amount in these blends. So, but keeping the amount of the water same, we get that these optimized aggregate has higher water to binder ratio. So we have to keep that in mind that this is a difference in these mixed designs. We looked at the fresh properties, and there was a slight reduction in the slump value for the case of the fly ash, but there was significant difference between the slump value for fly ash and 40% fly ash case and the 50% slag case. For air content, there was no statistical difference between the standard and the optimized aggregate systems, and the same thing with the fresh density that was around 2450 kilogram per meter cube for most of the samples. The compressive strength, so these are the compressive strength plot from 7 to 90 days. There was a bit of a reduction in the compressive strength at the 7 and 14 days, specifically for the fly ash case. However, as we approach the 90-day strength, we see that the slag, the case with the 50% slag and the optimized aggregate doesn't show any statistical variation in the compressive strength. There were some cases, but we hypothesized because we increased the water to binder ratio in these optimized aggregate cases, we do see a bit of a reduction in our compressive strength. The same pattern was observed in the modulus of elasticity, where we did see some reduction in the modulus of elasticity of the optimized aggregates, but they all remained in the range of 25 to 30 gigapascal. So they were in the standard range of modulus of elasticity for the concrete systems. The same thing with the split tensile test. At 90 days, the fly ash showed lower strength than the standard systems. However, the system with the slag, again, showed statistically similar results with the standard mixed design. And finally, the flexural strength. There was some statistical differences between the standard and optimized design for 30% fly ash, but there was no variation for the case of the 40% fly ash, and this remained same for the 90 days test results as well. So considering all these mechanical properties, we did see some decrease, but there was cases of 50% slag and 40% fly ash replacement with optimized aggregates where these values didn't change too much, and they remained very similar to the case of standard aggregate systems. Finally, what about their global warming impact? So that was being calculated. So what is global warming potential? It's measured a gas climate impact relative to carbon dioxide over a fixed time period. This study examines carbon dioxide, methane, and N2O converted to CO2 equivalents over 100 years. So the material-related GSG data was obtained from different literature for different material that is being used in the mixed design. So as you can see on the logarithmic graph, Portland cement has a huge difference compared to the fly ash and slag and aggregates. They literally didn't have any GSG emissions compared to Portland cement. So the amount of the cement do affect the global warming potential substantially. And this can be reflected in the results. So if you look here, we have a reference case just with 100% cement. We see, but just by partial replacement of the binder, you can see 20% drop in the global warming potential. And with the optimized aggregate, we can see up to 35% drop for the case of fly ash. With the slag, this number goes to 52% with the case of optimized aggregate and optimized concrete mixed design. Just with the just with the aggregate optimization, you can get up to 27% decrease in the global warming potential in these type of systems. So in conclusion, the particle packing theory can be used to reduce the global warming potential up to 25% with some loss of mechanical properties. We can use these the best particle packing doesn't have to be, the best case of the particle ticketing doesn't have to be the choice for your mixed design. You also have to look at the gradation and workability of these blends. And I would like to thank our group. Professor Reza Moini is here, our lab manager, and the rest of the group who helped in giving their intellectual thoughts in this project. I also want to acknowledge Port Authority of New York, New Jersey, Center of Advanced Infrastructure and Transportation at Rutgers, and U.S. Concrete, Heidelberg Materials, and Weldon Materials and Clayton Concrete Material for the supply of aggregates.